Okay, well, good morning. I work in the School of Veterinary Medicine at the University of Pennsylvania, so I have a very different viewpoint from the viewpoints that you've heard before. In fact, Dr. Lipsitch is quite wrong. The most famous example of eradicating an infectious disease using vaccination is not smallpox, it's rinderpest, a disease of cattle. And unlike Sarah, I would not have been wiping the face of that poor child who kissed the pig. I would have been wiping the pig's snout, because of course it goes both ways. First slide, please. Okay, so I'm going to be talking about chickens. And I'm actually quite excited by chickens. You may not be. So let's talk about, next slide, lions instead. So I'm going to talk about lions instead because I need to set up a model of a viral disease in lions first so I can explain to you why we model chickens in the way we model chickens. So next slide. In 1994, there was an absolutely appalling epidemic of canine rinderpest that was passed from the domestic dogs on the outside of the Serengeti National Park into the lions. And people often ask me, why on earth is it that you model diseases in animals? I mean, surely diseases in people are much more important. So in the break, get out your smartphones and go to Google and type canine distemper lions, click it, don't do it now. Click on video and watch the video from which this still is taken. Canine, infectious diseases are horrible things, but canine distemper is particularly horrible because it has a predilection for the central nervous system. And the animals that die of this disease die after several hours of the most appalling seizures. So look at that video and you'll see why I model infectious diseases in animals. Now, my veterinary students were equally appalled, just like I was. And so a few years after this, a group of them got together and said, well, is there anything we can do about this canine distemper epidemic in the lions? And so they said, well, okay, I mean, what sort of research questions are important? And there are two listed there in that green box on the left-hand side. One of which is it feasible to vaccinate lions? Well, you have all of the deployment problems. How are you going to get close enough to a lion to vaccinate it? But even if you solve that problem, the chances of getting close enough to all of the lions to vaccinate them, I mean, they're not great, are they? So the next research question is do we actually have to vaccinate all the lions? And that was the problem they were interested in. And I said, well, those kinds of research questions, next slide please, can actually be solved using models. Next slide. So let's talk about models for a minute. What you see in the center there is the model of an atom which I used over and over and over again when I was a school teacher. It's the planetary model of an atom first espoused by Niels Bohr almost 100 years ago. Now I show this model of an atom. What is it? What's the atom? Geez, my high school students would have known this. It's carbon, right? It's carbon, okay. Okay, now the great thing about a model like that is it illustrates several really, really important points about models. Thank you. The very first thing about models is they don't have to look like the thing being modeled. I mean, I know, for example, for a fact that electrons are blue, not green. I know that, but I know a nucleus isn't yellow. I mean, it's not yellow, is it? Yet this model is extremely useful because my high school students, at least, the 16-year-olds that I was teaching chemistry to, could look at that and could, even without knowing what it was, they could tell me what it did. They could tell me that that was going to form covalent bonds, not ionic bonds, because they could look at the number of electrons in the outer shell of that model. So a model does not have to look like the thing being modeled to be useful. A model, to be a good model, just has to be useful. You can omit all kinds of important bits of, in that case, biology, if you like, and yet still have a useful model. So models are aids to thought, and useful models are the best kinds of model. Now, the very first rule, and nobody's mentioned this yet, so I'm going to mention it, that I'm driving the cameraman mad. I see his left because I'm moving all over the place. The very first rule of modeling is that you model what you can count. Now, believe it or not, there are people who are paid to count the fleas on dogs. And you think, why are they paid to count the fleas? Well, the actual industry that's used, that spends money on destroying fleas on dogs and on cats and in our households is a billion-dollar industry. Now, you can, in fact, successfully count the number of fleas, and that doesn't work on dogs. You can count, for example, the number of nematodes in a cow, or in a cat, or in a dog. You can count the number of flukes in a sheep. You can do that. So if we're modeling those kinds of macroparasitic infections, we count the parasites and we model the number of parasites. If you're dealing with viruses or bacteria or parasitic protozoa, there's not a cat's chance. I use the term advisably. There's not a cat's chance of actually counting those. But what you can count is the number of hosts that are susceptible. You can count the number of hosts that are infectious, and you can count the number of hosts that have recovered. So when we model those kinds of microparasitic infections, we model the number of hosts. Next slide, please.
Yeah.
I have it. Oh, good Lord. Does it work? Okay. We don't even have to count the hosts. If we want to, we can count the number of farms that are infected. And even if they're fish farms, like the one you see on the extreme left there, those are farms that are farming salmon. There are infectious diseases that salmon get. What we don't count is the salmon, because we can't get in, a scuba deer guy. And what we can count is the number of farms where the fish are dying. I mean, one of the most famous examples of counting things other than hosts is Ira Longini's first study of the spread of influenza between cities in Russia. So we can model the changes in the number of cities with influenza in them or without influenza in them. So there are lots of things we can count, but if we can count it, we can model it. And what you do, and my biggest course in modeling at Penn doesn't involve any computers at all. We spit on computers, damn things, as you've seen. What we do is we obey these 4 little rules, and we just do this, and then we use our cell phones to do all the interesting stuff. So you choose a modeling format, and I'm going to talk about a very simplest modeling format, some of which you've seen already. Then you draw a flowchart just to get your head around the problem. Then you turn that flowchart into equations, and then once you've done that, you investigate the model behavior. And here's the basic idea about modeling. The idea is that the behavior of the model is exactly the same as the behavior of the system you're interested in. Next slide, please. Oh, no. Yes, draw a flowchart. So we count the number of hosts. There are susceptible hosts, there are infectious hosts, and there are recovered hosts. And that SIR model, the SIR model, that S not only labels the box, it also tells you how many hosts there are in that box. So the density of susceptible hosts, the density of infectious hosts, and the density of recovered hosts. Then what you do, having done that, you turn that flowchart into some equations. Next slide, please. There they are. I could teach anybody in this room in 30 minutes the recipe for constructing those equations from that flowchart. This ain't hard. It's a big secret, okay? It's not difficult. Anybody can do this. In another 30 minutes, I could teach anybody in this room to use that model to get some useful advice about control, at least within spitting distance of useful advice about control. Let's see if I can do this. So now what you do is you ask the question, and one of the most useful questions that models like this can answer is, what must be true for an epidemic to begin? Now you think about that. If you know what must be true for an epidemic to begin, you also know what must be true for an epidemic not to begin. And that's what clinicians do. That's what public health people do. They try and stop these epidemics from starting in the first place. So let's have a look at that. What is an epidemic? An epidemic is an increase in the number of cases. So this is the equation here, this one di by dt, that tells you the rate at which the number of cases changes. Now then, if those cases are going to increase, that di by dt, that rate of change in the number of infectious cases, has to actually be positive, doesn't it? Has to be positive, because if it was negative, the number of cases would be decreasing. So what's the only way that di by dt can be positive? It's ever so simple. That beta is has to be bigger than the sum of alpha I and sigma I together. That's the rule, and there it is. You see it up there, look. Beta S divided by alpha I plus sigma has to be bigger than 1. That's the rule, okay? And because we're interested in the point at which the epidemic is just about to start, we don't use an S there, the number of susceptibles. We use an N, which means the total number of susceptibles right at the very beginning. Next slide, please. So, man walks into a bar, right? I'm working here. Give me a chance, guys. Man walks into a bar, right? Next slide. Okay, there he is. He's in the Christmas hat. He goes through the door and he's suddenly feeling really poorly and he's spewing out virus. And everybody thinks, no, I'm going to stay for the party. I'm going to stay for the party. He stays for the next 3 hours. And in that 3 hours, next slide please, he infects that guy, and that poor lady at the back. He infects 3 people. And those 3 people represent the basic reproduction number, the number of cases that he causes. That's all that R0 is, that's all that basic reproduction number is. And obviously, any particular infectious individual's got to at least replace themselves and probably increase the number of cases in order for an epidemic to start. So that's why we're obsessed by R0. That's why there's this cult of R0 and I'm the high priest of R0. I mean, if you know that number, there's lots of useful things you can do with it. So next slide, please. And one of the things you can do with it is if you can calculate, and my students could calculate on their cell phones the value of R0 for that canine distemper epidemic in the lions in the Serengeti Park in 1994, they were able to predict, using the equation that Mark has already shown you, the proportion of lions you need to vaccinate. We've got a perfectly good vaccine for canine distemper. The reason you guys have never seen a case of canine distemper is because we vaccinate all our dogs. And if you haven't, do. It's a horrible disease. But that shows that we only need to vaccinate maybe 60% of the lions. We might be in with a chance there. Serengeti National Park. That sounds like an African name, doesn't it? It isn't. It's just a twisted version of the name of an English general who went in there in Victorian times and defeated the Ashanti tribes. You learn an awful lot doing epidemiology, don't you? Okay, next slide, please. So, there's a problem with that model, though. The problem with the model is it assumes that all the lions in the Serengeti National Park, and the Serengeti National Park is a big, big place, that all those lions mix freely. That any infectious lion has the same chance of infecting any susceptible lion as any other infectious lion. That's not true, is it? It isn't true, because lions walk around in prides like you see up there. They're in groups. Now, maybe those prides interact, but most of the interactions are within the pride, right? Okay? I mean, look, we don't have lions in the United States, but we have feral pigs. And feral pigs wander around in prides just like that. We call them sounders, but it's the same thing. And they are seeping up from the south, up the watercourses from the south, like a sort of black, furry, snuffling plague. But you try and model disease in feral pigs, and you've got the same problem because they're in groups, and most of the interactions are within the groups. So that's clearly a problem with the model that my students show. Now, you imagine chickens, and at last we get to chickens. You imagine chickens, and chickens live in houses like that, and those houses don't move, do they? Hence the title of my talk, Fixed Networks. It's all very clever, you see. Next slide, please. Can we go forwards? There we go. Now, the other thing my students said, you know, they're vets, they were pretty experienced by this time. They said, well, I mean, if you run that model in Berkeley Madonna, wonderful program, buy it now, it's dead good, right? If you run that model in Berkeley Madonna, if you don't change the parameter values that you use, you always get the same answer, always, always, always. And they know that that's not true. Look, you've seen lots of these sequences before. These are recurrent epidemics of measles in this particular case in London. Those epidemics, one year after the other, were all different. Now, London didn't change dramatically from one year to the next. And one of the reasons, not all the reasons, but one of the reasons those epidemics are different is because of the operation of chance. So there are two things, if we're modelling chickens, we have to take account of. One, the chicken houses don't move. And two, we have to take account of the operation of chance. So we're going to be talking about spatial models involving fixed networks of chicken houses in which chance is operating. So next slide, please. Now, this just shows you this happens to be Canada, not the United States, but this is the Fraser Valley in British Columbia, and each one of those yellow arrows is pointing to a series of chicken houses. So this is the kind of map that we operate on. This is the kind of network that we've got. So next slide, please. And what we have originally, before we even detect something bad is going on, is what you see there on the left-hand side. We see each one of those billiard balls there represents a chicken farm. Maybe the red ones are infectious, the grey ones have already been depopulated, so that is to say all the chickens have been killed to save them. And the green arrow, the green billiard balls there are the chicken houses that have not yet been infected. Now, before we know something bad is happening, those chicken houses are connected by commercial links, you know, trucks, people who work in several houses, the guy who carries the cockerel around under his arm to inseminate the layers, you know. That's not a joke. That's how it works, okay? So those, and then we discover something really bad is happening. And the very first thing the federal or the state government does is says, thou shalt not move. And that's what happens. And so all of those white lines disappear. So when I come into the act, what I'm dealing with is this. Because this is the only point at which we actually start controlling the epidemic. We've got a fixed network. And now we're talking about sort of all of those illegal movements, those shadowy at-night movements that nobody knows about and that we can't really quantify very well. And things like wind-blown virus blowing out of the poultry house and so on. Next slide, please. Okay. So what do you do when you're trying to look at what it is that governs transmission from one poultry house to the next? Well, you go to straightforward classical epidemiology and you look at case control studies. And what case control studies tell you are what are the risk factors for infection? What increases the probability of one house being infected? And they're pretty obvious, actually. So if you've got a large commercial facility next to an infected large commercial facility, it's going to get infected much more, with a much greater probability than one that's, say, 5 or 6 miles away. So proximity matters, number one. The other thing that matters is the size. The bigger it is, the leakier it is. So size and proximity matter. Next slide, please. So what you do is you create a transmission kernel that looks like this straw hat. The Infectious farm is right at the peak of that straw hat. And if you like, the probability of that farm infecting any other farm around it depends upon how high that straw is above the ground that it's resting on. So if you're a farm very close, say here, there's a very high chance of your being infected by the farm at the peak. And if you happen to be a farm right at the very edge out here, there's not much chance of your being infected. So what we do is every day, for every pair of farms in that entire network, we use that straw hat, that transmission kernel, to calculate the probability that the infectious farm will infect the susceptible farm in the pairing. And then what we do is we ask the computer to generate a random number between 0 and 1. And if the random number, in this case, is less than 0.3, then what we say is, well, okay, infection has occurred. And if it's greater than 0.3, we say it hasn't occurred. So we've got chance in there, right? We've got a fixed network. We've got an empirically derived, that is to say, from the data, model of the way transmission works from a single farm, and then we put chance in there. Next slide, please. So models like this can be used to answer all kinds of really, really useful questions. Now, we don't vaccinate a great many infections of chickens for very good and cogent reasons, but some we do. And suppose we had an appalling outbreak of a viral disease in chickens, and there was a vaccine available at some company, and the extension agents, that is to say the people who work for the United States Department of Agriculture in the county or in the state where the disease has occurred, have the job of disseminating this vaccine. Now, how should they do it? Should they just send it to their friends first? Should they just, set up a station sometime? It could be a school, it could be at the local county offices, it could be, these pods, these points of distribution. Could they just let the poultry farmers come in and get the boxes of vaccine and get the poultry farmers to distribute it? What should they do? Well, what we know is, from lots and lots of simulations like this, is that if you just let people come in at random and say, there's the vaccine, take it, that's a dreadful, dreadful way of vaccinating. Because if you vaccinate according to the things that you know increase the risk, like size or proximity, you have a dramatic effect on the threat of that epidemic to your production. If, on the other hand, you just vaccinate at random, you let people do it as a matter of convenience, it takes much, much longer to have any kind of effect. And that's when you explain to people, they think, well, that's obvious. Why do you need a model to do that? Well, the fact is, it isn't obvious until you model it. And that's the terrible experience of most modelers. When you explain the outcome of the model, people very often say, well, it's obvious. And you're saying to them, well, why didn't you think of that 3 days ago? Right? It's wholly obvious when you've used the framework to think about it. Next slide, please. One of the other things you can do is you can talk to the police departments, because the federal government has an action plan for all of these diseases in animals. And one of the items in that action plan says that every farm must have a constable or a policeman or a state trooper at every exit to the farm. And then if it's more than one farm, you have to draw a circle around the farm and you have to set up roadblocks at all of those roads. So what we do is we run our models and then we put the circles around the farms and then we say to our local police, all right, and I'll come over to this side because you seem to be getting pretty short shrift, all right, here's a map, right, there's a map, there are the blue circles, count the number of roadblocks that you've got. Every time a blue circle intersects a road, there's got to be a roadblock there because the federal government says so. And the police department say, we've only got 4 policemen and 3 cars. True. And so what you do is you say to them, well, okay, why is the government saying that you should do all of this? What is it they're trying to prevent? And you talk about what it is that's trying to be prevented. And then you say, okay, you can't obviously do what's in the action plan, but you know what the objective is. Now you're the locals. You tell me how you're going to achieve that. And I guarantee within an hour they've got a plan that's feasible. But if they'd just seen that manual, if they'd been told that, Lord, there's an outbreak, open the manual, this is what we've got to do, can you imagine their response? So models are useful as training tools. They work really well as training tools. Next slide, please. And they can help you advise policymakers. And what you very quickly learn if you're talking to county or state officials is that they all have different definitions of success. And as a modeler, I can tell you, if you don't know what that definition of success is, you are up the creek without a paddle. You really are, because you can get a perfectly good control policy, but if it doesn't match the definition of success, you have to start all over again. So one definition of success might be to keep the epidemic as short as possible. Another might be to achieve disease-free status as quickly as possible, and that's a little bit different for reasons I'll explain later on if anyone is interested. You might want to confine it just to a given county or a given state. You might want to use a control method that minimizes losses to the populations, because one of the things that vets always do is they operate just like firemen in a forest fire. They don't just spray water on the trees that are burning. They'll cut down trees that aren't burning to stop the fire spreading. And vets do exactly that. To minimize the cost of control. Is it cheaper to kill animals or is it cheaper to vaccinate them? They'll minimize the risk of a major outbreak. Okay, well, I mean, do I want to do something which I don't care how long this outbreak lasts, provided it's small? I don't want a big outbreak. Or, and this is a big one, to minimize pushback. You don't want protesters at the street. You don't want animal rights activists saying you can't kill the chickens. You don't want the state having to get a truck loaded with dead pigs and drive it into the middle of Philadelphia to a landfill in the middle of the night, in the middle of Center City, because that's the only way you can dispose of the animals if you're to avoid the protest groups. True story. True story. To minimize pushback is a really, really important part of offering advice. Next slide, please. So let's talk about one particular outbreak in British Columbia. It happened over there in the Fraser Valley, that little red square that you see. Next slide, please. This is a fascinating example of the way in which these definitions of success changed with time. Originally, when there were just 2 farms infected, that red arrow, what they did was to say, okay, we're not going to upset the producers. We'll just kill all the chickens in the chicken houses that we know are infected. A few weeks later, next slide, please. They put this big ring around the original outbreak. Next slide, please. And they suddenly discovered they had more farms in that ring. So they thought, right, what we'll do is preemptively cull. Now, preemptive culling is when you kill animals in a defined area, even if they're not infected. You don't care whether they're infected or not. You just go in and kill everything. So a few weeks later, when the number of cases increased a bit more, they said, right, we don't care about inflaming the producers. We're going to stop this now. We really are. We're going to stop it. So they decided to preemptively kill all the animals in that original yellow ring. Next slide, please. So cull all the farms. We don't talk about killing in veterinary medicine. We talk about culling. It's a nicer word somehow, isn't it? But it's actually killing. It's culling. Right. Kill all the farms in that high-risk zone. Unfortunately, a few days later, there were some infected farms discovered here, and even, goodness help us, right out there. Next slide, please. And so by this time, gigantic increase in the number of cases. The Canadians were totally thrown by this, and they said, right, we've just got to stop this now. Because there were dozens, literally dozens of countries who were ceasing to trade agriculturally with Canada. Dozens of countries who were ceasing to trade. And so they said, right, we're going to kill every single chicken in that entire map. Millions and millions of chickens. Because their definition of success had changed from don't upset the farmers to let's just get this done as fast as possible so we can get our trade back. Next slide, please. And who wouldn't want to think about what is the best way of doing this? Because depopulation is a very grim process. The guys with the carbon dioxide trucks roll up. You take duct tape and black plastic. Those of you that remember 9/11, do you remember the duct tape and black plastic? Yeah? Well, the way vets use duct tape and black plastic is to seal up the doors and windows of the poultry houses. And then what they do is they pump the carbon dioxide into the poultry house and they wait about 4 hours. And that's what happens. Then they leave the poultry in there for 4 days to allow the poultry, as we say, to compost. That means the temperature rises high enough so it kills the virus. Then we go in there with a front loader, we get all the chickens up and we spread them on the fields. You are eating vegetables and crops that have grown on the bodies of dead chickens. It's very, very efficient. But it's a horrible process, and we spend a lot of time trying to work out how we can do this by minimizing that kind of thing. Next slide, please. Okay, the effect of preemptive ring culling is very, very subtle indeed. If you put a circle around an infected farm and start culling all the farms in that circle, and then you do that for every subsequent infected farm you can make, you have a real problem. How big should the circle be? How big should the circle be? And one of the things you realize is if you mess it up, you can achieve one definition of success and fail at another. This is a dreadful slide and I apologize, but that blue line at the top represents the number of farms you'd have to cull, depending upon the horizontal axis, the width of the circle. Now what you notice is, if you look at the bottom slide, is there is a particular width of circle where you actually reduce the number of farms you want to cull, but you increase the duration of the epidemic, that bump above the red line. You're increasing the length for which that epidemic actually is in play. Now that's two contradictory definitions of success. Next slide, please. The other thing you very quickly realize if you're using these fixed network models is where the first case occurs is really, really important. If it occurs, for example, in one of those very densely populated areas, well, just put your head in a brown paper bag and give up. You're doomed. You know, you are in real trouble. If it occurs in one of those less populated areas, you're in with a chance, and you can use preemptive culling. If it occurs in a densely populated area, give up the preemptive culling idea. It's just not going to work for you. Just do the best you can. Next slide, please. The other thing you learn is surveillance is so important. One of the best things that counties and states and federal governments can do is to enact really, really good surveillance. Because the horizontal line on that slide there is the number of infected farms before you realize there's anything bad going on. Now what you'll notice here is if you look at that green line, there is an optimum radius for the circle that you put around a farm for preemptive culling. But once you get above, say, 30 farms already infected, nothing really works. You actually make things worse. There is no optimum radius for preemptive culling. You have to go back to just culling the farms that are infectious. Next slide, probably the last slide, I think. So there are some depressing conclusions too. And this is where I'm going to finish. In the absence of a detailed foreknowledge about the quantitative characteristics of transmission, particularly the shape of that straw hat, and the distribution of farms, in other words, that map, and you cannot get maps of where the farms are, believe it or believe it not, there is no reach-back culling strategy that you can guarantee to a policymaker will always be optimum in terms of any of these definitions of success. There just isn't. Next slide, please. The factors that matter are the shape of the transmission kernel. Is it narrow? Is it wide? How far away the site of introduction is from areas of high livestock density, and the number and location of the premises infected before detection. Next slide, please. And we don't know any of that until it happens. Now, if we know that, we can use models sensibly to advise policymakers. If we don't know that, we're doing a lot of what I do, which is hand-waving. So if you're in my position, what would you tell the policymakers? And as it says on that slide, and it's my last remark, that's not a rhetorical question. What would you do? Thank you.
Hi, my name is Wilhelmina from University of Maryland. My question is, if the RO for a particular infectious disease is, say, 3, does it remain constant throughout the duration, or do varying susceptibility levels in the population change that?
Okay, so very good question. For those of you who didn't hear it, I was asked the question, does the basic reproduction number, the R0, stay constant throughout the progress of an infection? And the answer is no, if you're talking about the basic reproduction number. The basic reproduction number pertains just at the point where the virus is just about to get in to that population. That's a fixed number. The 0 in the R0 refers to time. It's time 0. Okay? That is a fixed number. But we can measure the reproduction number at any time during the progression. And that's what Mark called the effective reproduction number. And that does change. And it will decline. It will go down and down and down and down and down. If we're talking about an epidemic, you have put more new wood on the fire, no new births, it'll go down and down and down. Eventually the whole epidemic will fade out. And it is the clinician's job, it is the public health person's job to create the conditions that make that reproduction number get below 1 as fast as possible, because that is our definition of success. Okay? Anything else?
Hi, my name is Binta. I'm from Montclair State University in New Jersey. First of all, I want to say fantastic talk. I liked your enthusiasm. I was literally on the edge of my seat. And my question is, how would you start, or where would you start looking or thinking about making your own model, you know?
Okay, so the question is, for those of you who didn't hear it, when in any modelling, I think, in any modelling activity, where do you start? Okay, what I always do with my vet students who, you know, they say to me, look, if we wanted to do math, we wouldn't be vet students, right? But, you know, they get it. They eventually get it. And what we start with always is the flow chart. Because what they end up with is a flow chart with 15 or 16 boxes in it, because they're vets. They like the detail about the disease, right? And then we say, okay, which bits of that are important to the kinds of question you're interested in answering? Because you must always define very early what the research question is. And they can usually get that flow chart down to about 4 boxes. Then once you've got 4 boxes, you can write a simple deterministic equation, and that will just clear away the brushwood. Then you can go on to the more sophisticated models. You know, it's sometimes represented that there are 2 schools of modelling, those who do the reductionist simple models and those who do the gigantic black box supercomputer models. I don't belong in either camp, actually. You make the model as complicated as it should be in order to answer the question asked. But it just makes sense to me to start with a simple model if you're new to the subject, because it teaches you. Models teach you stuff. One of the biggest values about models, they teach you stuff. And you can go from one model to the next, incrementally, understanding how each thing you add to it affects the behavior of the model. That would be my advice. Anything else? We're getting very close to the coffee break. And I need a coffee, trust me. Yes, sir.
So, Dom Acharya from Mercer's University, Pennsylvania. My question is like no compensation to culling the farms causing the spread of infectious diseases across the farms?
Can you say the first part of the question again?
Like a non-compensation, like when a farm is called,
yes,
the government does not pay the farmers.
Yes, no. Okay, so the question is about compensation. Yes, so compensation for culling farms is an interesting question, especially if you look outside the United States. Inside the United States, the federal statute is very clear, and I quote this to my students all the time. What it says is, in the event of compensation having to be paid, the farmer will be paid up to, important phrase, up to the fair market value of the animal. And then there's another phrase, if the funds are available. Right? If you look in other countries, like Indonesia, for example, is a great example, where the compensation for culled chickens is too low, then what happens is when the slaughterers come into a village, everybody takes their chickens and they hide them. On the other hand, if the compensation is set at too high a level, people who have chickens that are not diseased or from outside the area are bringing them in to be killed. What you very quickly discover is that criminal activity, fraud, is a constant companion of any animal disease epidemic, and compensation is a big element of that activity. Did that answer the question?
Yeah.
Yes? Talk to me if I hadn't completely answered it at the break.
Okay, I think that is it for questions, but I just wanted to say two things. First, also for the presenters, because who knows what emails they read of ours, that lunch is a networking lunch. So ideally, all your questions, like I want to promote them. So different tables will be the different speakers. So when you go to lunch, sit down with speakers, you have extra questions. I know that Sarah didn't get a lot of time for questions, so that's your opportunity if you don't get them here. Second is that we really need to keep on schedule. So I know we had this glitch earlier, but we are going to come back at 11:05. So there's a lot of people getting on flights today, so we want to make sure we stay on schedule. Thank you.